Okay. All right. So thank you all for coming to the last one. So let me begin again with a quick recap of what we talked about in the last lecture, and then we will talk about something which is Wasserstein density estimation as our last topic. So let me recap where we were. We were talking about the statistical optimal transport setting. So what's the idea here? You're rather than given direct access to two distributions and being asked questions about the OT map, now we're only given sample access. So you should imagine we're kind of trying to apply some of these algorithms to data, and we want to understand how well do they perform, or which algorithms are better or worse. Then somehow the statistical framing is the natural one. So the setting is going to be, we'll sample n samples from the distribution mu and n samples from the distribution nu. And we can ask various questions now. One of them would be, can you say the distribution mu is absolutely continuous? So there is an OT map between them. Can you estimate it from the samples? So how well can you, given just the samples, estimate the OT map? You can ask how well can you estimate the Wasserstein distance? So can you tell if the two distributions are close or far in the Wasserstein sense? The other, which we'll talk about a bit today, is can you construct estimators of the distribution mu, say? So can you construct a mu hat such that the Wasserstein distance is small? So this is like, can you estimate the distribution under the Wasserstein loss? A different thing that you might care about is to try to estimate barycenters. So for instance, if you have many distributions, you might say, what does their average look like? And in the case when you have samples, you might say, how well can you estimate the average of a collection of distributions just given samples from them? Um, in the last lecture, we mainly talked about estimating the transport map. We saw that maybe, okay, broadly, there are two strategies that people have considered. One is to make the observation that uh, the semi-dual is a functional that is optimized at something called the Brenier potential, whose derivative or gradient gives you the transport map. So there is some function, if you manage to optimize it, then you would get something whose gradient would give you the transport map. And this semi-dual had this nice property that it was just linear. It was an expected value of some pair of functions. And so it makes sense to try to replace this expected value by an average. So given samples, you just take an average and then minimize that corresponding empirical semi-dual functional. So this is like the empirical risk minimization principle. And that will give you an estimate phi hat, and you could take its gradient. These estimators are sometimes called dual estimators because they're based on the Kantorovich dual to the OT program. And the other estimators, which are maybe a little bit more natural, just say you follow one of two things. They follow a plug-in principle. You're trying to estimate the OT map between mu and nu. So maybe you first construct a good guess of the distribution mu and a good guess of the distribution nu. And then you find, and we'll call them mu hat and nu hat. And then you find the OT map between those estimates. So the OT map between nu hat and mu hat is your guess for the optimal transport map t hat. Right. So that's one thing. Those are called plug-in estimators. You can construct these density estimators in any way, and then you can ask, okay, how good is t hat as an estimate of the underlying transport map? The other thing that one might do is to say, we'll use the empirical measure. So we won't do any density estimation or any clever density estimation. We'll just use the empirical measure. We'll compute a transport map between the empirical measures. This is just a matching of the X samples to the Y samples, and then we'll extend that matching using the nearest neighbor principle. So these are various different choices that one might come up with for ways to estimate the transport map. We then talked about how would we measure if we've done a good job. So we defined some sort of risk function. So the risk is just how far is your guess from the truth integrated over against the measure mu. So it's some average squared distance between your transport map estimate and the true transport map. And then we saw some concrete analyses. So maybe the main high level takeaway was that in order to analyze these kinds of estimators, what has to happen is that we have to argue somehow that the program that we're solving to get these estimators have some sort of stability. We're somehow perturbing their input arguments, and we're trying to say something about the output of these optimization problems. So it better be the case that these optimization programs are in fact stable to perturbations of their inputs. And we showed one such stability bound, which is just to say the semi-dual, at least if you're looking at strictly convex and smooth functions, it will grow quadratically around its minimizer. So that is, you should imagine that if I looked at this semi-dual functional, so I've defined it up here, it's the integral of phi against mu plus the conjugate of phi against nu. This is some functional that we're trying to minimize. But let's say we looked at what is its value at some point that's not the minimizer. And the point is that it grows very fast around its minimizer. And so as a result, because it grows very fast, if you approximately minimize this function, you will get very close to the true minimizer itself. And so this is the basic structural fact that we proved last time, which was that the semi-dual functional grows very fast around its minimizer. And this we saw immediately implied that this empirical risk minimization principle was a sensible one. And we showed some bound that said, okay, if you make various assumptions, then it is the case that the dual estimator, which is this thing over here, will be quite close to the true transport map with some rate that depended on how many candidates you're picking from logarithmically and something like 1 over square root n. And so we saw some analysis of a dual estimator. And the basic thing was once you have a stability bound, you can combine it with some standard concentration inequality and get an analysis for it. And then we ended the lecture talking about plugin estimators. I just stated a result and we didn't prove it, but it's not too different from the other one to prove. So the basic setting here is we're going to say we have a pair of distributions mu and nu. They're linked via a function grad phi 0. That's the OT map. And we'll make the assumption that phi 0 is smooth and strongly convex. Then we said for any mu hat and nu hat, we demonstrated that we could construct a t hat. You find the optimal coupling between mu hat and nu hat, and then from it, you extract a transport map t hat. This is the barycentric projection. And that transport map will have this property that its distance to the truth will be upper bounded by the Wasserstein distance between mu hat and mu and nu hat and nu. So as long as you can estimate the two distributions well in the W2 squared sense, you will also estimate the transport map well. So this is just saying that this optimal transport program is very stable to perturbations of its arguments as long as these perturbations are small in the Wasserstein sense. Okay, so let me pause here and see if there are questions. Otherwise, we'll jump into some new things. Okay, so then
Shiva, a quick question for you.
yeah.
How easy or difficult is it to compute this empirical map he had?
Uh, Here, in full generality, it's probably not that easy. So between the actual empirical distributions, it's just a linear program which will run in O of n cubed time or something, right? So there's a
Right.
simple, reasonably fast algorithm. If you if I just gave you arbitrary measures and said compute the OT map between them, that's probably not so easy. The best thing that we would know how to do is you sample that measure or discretize that measure heavily and like for some large value of n, and then you compute the resulting OT map between those two discretizations. So in some sense, this is not, for general measures, this is not a very practical thing to do.
Mhm.
Okay.
Okay.
Right. Okay, so the focus for today will be to answer the question, okay, how do I make the terms on the right-hand side in this bound small? So here's the setting we're going to think about. We just have a single measure and I sample from it. And I would like to construct some mu hat so that, let's say I don't know, for us, you can take any thing, but let's say the WP distance between mu hat and mu is small. This will be our question for today. And maybe the first thing to observe is that under relatively mild conditions, it is the case that the empirical measure, mu n, is already consistent. And this should be somehow contrasted with regular, more familiar, say, smooth density estimation. It's not that if you care about density estimation, say in the L2 loss or the TB loss, it is not the case that the empirical measure is consistent. But here, for the Wasserstein distance, it is in fact the case that the empirical measure is already consistent. And so we'll see, okay, what does this mean? How fast does it converge and so on? And maybe the other question one might wonder is it the best possible estimator? And if not, can it be improved? How can it be improved? When can it be improved? And so on. And so those are some of the questions, at least we'd like to get some sense of today. So let me first start off by telling you a result about the empirical measure, and then we will see how one proves that result. It's a fairly fundamental result. It probably goes back to Dudley in the 1960s. So that'll be our first thing to try to uh, think about. So we just want to say, okay, our estimate is just going to be the empirical measure, and we just want to understand what rates of convergence does it get, and are they good or bad? So here's the theorem. You can generalize this in many different ways, but maybe this is the simplest setup. So I give you x1 through xn from some distribution mu, and let's say that mu is supported on some compact set, which we'll take to be the unit cube. And now we're just going to ask, okay, what can you say about the empirical measure? And this is the result that is known. The WP distance between mu n and mu will be upper bounded by, and there are sort of three sets of rates. So the rate when the dimension in a sort of high dimensional case, so when d is bigger than 2p, it looks like n to the minus 1 over d. The rate when the dimension is small looks like n to the minus 1 over 2p. So this is when d is less than 2p. And then there's some critical regime where the rate when d is exactly equal to 2p, and there's some interesting log factor here that people have wondered about for a while, but maybe the rate that one should get kind of looks like this. Okay, so it looks like n to the minus 1 over d or n to the minus 1 over 2p, but there's some extra log factor. Okay, so maybe just to get some insight into what's going on, you should think about the case when p equals 1. This is the case that we'll work on mostly today. So this is the W1 distance between mu and mu. So the theorem just says that when in one dimension, you get 1 over root n rates when d is 1. When d is 2, you get something that is just slightly worse than root n. And then when d is bigger than 2, you get n to the minus 1 over d rates. Okay, and these rates exhibit some very clear recursive dimensionality. That is to say that uh, they degrade quite badly or exponentially badly in the dimension. And maybe this shouldn't be too surprising. You are estimating some non-parametric object with a fairly powerful notion of distance. So the Wasserstein distance is quite a useful, powerful notion of distance. So you should expect somehow these non-parametric rates of convergence. And maybe the surprising aspect of these results is just that you can get consistent estimates without assuming any structure on mu other than in this case that it's supported on some compact set. Okay, so let me pause here for 1 second, see if anyone has questions.
I have a question. So if
Yeah.
mu were not compactly supported, is it still not a consistent estimator? Maybe the rates are not this, but is it still a consistent or?
You have to be a bit careful. So if you assume some kind of moment conditions on mu, then yes, it will be a consistent estimator. If you assume no conditions, let's say it doesn't even have finite, say, second moment, then you may not be able to estimate all of these WPs consistently or estimate under these distances consistently. So under some mild moment conditions, it is true that it is consistent. The rate will degrade depending on the moment assumption that you make.
Okay, thanks.
Yeah.
Now, are these just upper bounds or are these also lower bounds?
Yeah, so these are also lower bounds. So these are all tight for the empirical measure. They are also tight in some minimax sense, which is just if I make only these assumptions on the distribution, then there are no estimators that can improve on this. So yeah, they're all tight. including, and maybe this has some long history, but including all of these log factors are known tightly.
I see. Thanks.
Okay. All right, so then let me just tell you a few other variants of these types of results. Maybe these are somewhat pessimistic results, but you can get slightly more optimistic results in some cases. So there are, again, this is a relatively large literature, but there are many, I'll call them intrinsic dimension variants. So what does this mean? The effectively in all of the bounds above, you can replace the dimension by some other notion of dimension, by something. There are many that will work by some version of intrinsic dimension of the measure mu, of mu. And I will tell you one such variant, but maybe the intuition you should have is just if mu happens to be supported on some low dimensional manifold, then it will be the case that you will get faster rates where I will just replace the ambient dimension by the dimension of the manifold. And the same empirical measure will get you these faster rates. And okay, so if you haven't seen them before, maybe, okay, one notion of intrinsic dimension that works here is to take um, the epsilon covering number of the support of mu. Right? So there are even stronger versions of these. You don't have to cover the entire support and so on, but let's just stick to this. So you can imagine covering the support of mu with epsilon balls and saying how many of them do I need? And looking at the scaling, so this will typically scale with epsilon. If you're in Euclidean space, it looks like 1 over epsilon to the d. So if I divide this by something like minus log epsilon, and this has some value, this, let's say it is some critical number d star, this d star suffices. So that is, as long as you can control the quantity on the left by some notion of dimension, that notion of dimension will enter into your rates of convergence of the empirical measure to the ground truth. And you can think, if you're familiar with either, I don't know, the Minkowski dimension or the Hausdorff dimension, this is some version of those kinds of quantities. Let me pause again and see if there are questions. The basic takeaway is just, if your measure is supported on a lower dimensional set, then you will get faster rates of convergence, and the empirical measure will adapt to this.
So if the support is a manifold with some dimension d star, will this this particular number also be d star?
As long as your manifold has some sort of bounded curvature or something, like it can't be like a space filling curve, but yes, under some conditions, yes, this notion will match that.
Yeah, thank you.
So Shiva, in some sense, is Wasserstein a good distance in this sense, in the sense that we had other notions of probabilistic distance, empirical measure with the true measure, those would behave, those would be harder to estimate? It have a larger convergence rate?
So you have to say what you're thinking of, like what distance are you thinking of when you say this?
So maybe Kullback, Leibler, total variation, these popular ones.
Yeah, so in some sense, those are all essentially not estimable at all. That is, if I said estimate the KL from samples or the total variation from samples, you need some additional assumptions to do it. You need something like the measure has to be smooth and bounded away from zero or something in order to estimate those distances consistently. So in some sense, yes, the Wasserstein distance is easier to estimate than those things. Um, it depends somehow on your use case. There are, for instance, even easier distances to estimate than the Wasserstein distance. You could look at something like the MMD, which is you can define an integral probability metric over a smaller class of functions. So maybe there's some trade-off, which is how expressive is the distance and how easy is it to estimate. And depending on your use case, there are different versions of this trade-off that will be useful. Like, I mean, you would pick a different distance based on what you're trying to do with the, yeah, what you're trying to do at the end of the day.
Right, right. Thanks.
Yeah. Okay, so then let me also say one more thing, which is there's also some, and there are very few such results known, but you can ask what happens in the smooth case. So what is the smooth case? Let's say the measure mu is S holder. Again, I won't even define it, but what I mean by this is that say S is an integer, then I mean that the mu has S bounded derivatives. Let's say in the L infinity sense, right? So something like this is true. You can look up the rigorous definition somewhere, but it basically means that the measure mu is smooth in the sense that it has S derivatives and all of them are bounded in L infinity. So you can say, okay, in this case, we know if I make this kind of smoothness assumption, we know that usual non-parametric rates improve. The task gets easier somehow, and we can ask if is the same thing true here, and does the empirical measure still get us faster rates of convergence? So let me tell you what the answer is. So it'll turn out that the minimax rate, the best possible thing that you can hope for, looks a little bit better. So it looks like n to the minus half. So let's actually let me do the case when p is 1. It's a little bit easier to compare. Looks the same when d is 2 as well. So the d equals 1 and 2 case exactly match. And then when you're in higher dimension, rather than get an n to the minus 1 over d rate, you get something which looks like n to the minus s plus 1 over, say, 2s plus d. So this is when d is bigger than 2. So this rate of convergence improves as I assume more and more smoothness. And maybe you should compare this to the usual non-parametric rate would be something like and maybe, okay, if you're not familiar with non-parametric rates, the way you should think about, say, the usual non-parametric rate, it's something like how well can you estimate the distribution in the TB sense. That would be something that looked like n to the minus s over 2s plus t. Right? So the comparison between these two is that when the smoothness goes to 0, you cannot estimate something like the TV. So the usual non-parametric rate will just become some inconsistent thing. That is, it'll say that you cannot estimate your object. Whereas the W1, as s goes to 0, will back off to this n to the minus 1 over d rate. So you can still consistently get some estimate of your distribution in the W1 sense. And it is always the case that the W1 rate will be somehow slightly faster than the non-parametric rate. And the other question that you can ask is, okay, what does the empirical measure get this? And it'll turn out the answer is no. So the empirical measure does not adapt to smoothness, cannot take advantage of smoothness. And instead, one has to use something like a kernel or wavelet estimator. So that is, you have to smooth the empirical measure appropriately, and then that would be a better estimator of the underlying distribution in the Wasserstein sense. So if you haven't seen this before, maybe I'll just quickly tell you what a kernel estimator is. It looks like you take the empirical measure, but rather than use it directly, you convolve it with some kernel with some bandwidth h. Okay, and so it sort of smooths out the empirical measure with an appropriate kernel with an appropriate bandwidth, and those are the kinds of estimators that achieve these faster rates of convergence. So it will, if you care, it will look like it will look almost like the empirical measure, but just smoothed out a little bit. Maybe So that is mu hat at some point, little x would look like this. Okay, let me pause again here for a second and see if there are questions about the smooth case. Okay, so then let me keep going, and then we'll yeah, okay. So let me just briefly say that all of these results have implications for transport map estimation. So I'll just mention this, but they are the obvious ones. So the first one is if you are estimating the transport map between a pair of smooth distributions, then you can get the rate that we said somehow t hat minus t0 in this L2 mu sense will scale like, so the square, so even the W2 distance looks like what I wrote up here. So the square will scale like n to the minus 2s plus 1 over 2s plus t. Right? So this is if the measures are smooth, that is if mu and nu are smooth. The other one that is interesting is with essentially just moment assumptions, the nearest neighbor estimator will attain some rate of convergence just because the empirical measure is already consistent. Under very minimal conditions, you can consistently estimate the transport map as well. And you will get this n to the minus 1 over d rate squared. So this is just, say, mu and nu have bounded moments and satisfy the other regularity conditions we've talked about. Okay, so the takeaway here is just you can estimate the transport map at some rate, and it inherits this rate from the difficulty of Wasserstein density estimation. So under some very mild conditions, you can consistently estimate the density, and so you can also consistently estimate the transport map under those conditions. Okay,
So
so now,
Shiva,
yeah,
so Shiva, in the first condition, that's under for some kernel being used, right, to estimate the distribution.
exactly. So this is t
Yeah.
hat is the OT map between the kernel density estimate mu hat and nu hat, say.
So
Yeah.
does it matter what kernel you use? Gives.
Yes, it does. I mean, yeah, it does. So in general, if you want to get rates and the smoothness is bigger than one, then you have to use something called a higher order kernel, which may basically, if you integrate it against low order moments, it vanishes. So it has to satisfy some basic condition like that.
Okay.
So, okay, I'll just write it here. You typically, if you want to obtain these faster rates of convergence, you would use something called a higher order kernel. But beyond that, it doesn't matter too much which higher order kernel. The bandwidth matters a lot, but other than that, the kernel itself maybe doesn't matter that much.
And there are computational consequences to estimating t hat
Um,
because now it's not empirical, now it's not no longer a linear program.
yeah, so that's right. So that is this, you should, maybe it's not the most practical estimator. You can resample a kernel density estimator easily. So the thing that one might do in practice is you would first compute mu hat by kernel density smoothing, and then resample it many times and then compute something like the in-sample thing from that. So then I would sample x tilde 1 through some x tilde n from mu hat and then use something like this nearest neighbor estimator on this. And you can show that this will work as long as you take n large enough. So you need the smoothing to construct a reasonable density estimate, but then you can resample that density estimate so that is sort of discretize the density sufficiently finely and then compute it. But again, not the world's most practical estimator now.
But you'll get the convergence rates, the smoothed convergence rates. Wow.
Yeah, you'll get the smooth convergence rates, but this n will have to be very large.
Okay.
Okay, so all right, so now let's try to see how one proves these different bounds, and we'll focus mainly on the W1 case, and I'll show you two of the canonical arguments that people use in order to prove, say, the empirical measure bounds that we talked about just now. So we'll focus on W1. And then I'll tell you how these generalize to other things at the end. So for W1, the thing that is convenient is that we have this nice dual representation. So let's suppose we think about W1 between the empirical measure and the truth. Right? We already know what this is. It has this dual representation that it's the supremum over one Lipschitz functions of the expected value of that function under mu minus the average under mu n, right? So that is, it's the integral f d mu minus the integral f d mu n, right? So this is just the dual representation of W1 that we derived a few lectures ago. But this itself it should look very familiar to everyone. It is just what we would call an empirical process, right? So it is the expected value of f minus the average of f. Right? So this is an empirical process. So what does that mean? It's an average minus an expected value indexed by some class of functions. And we're saying, what is the supremum of this empirical process? And this is maybe one of the central things that people have studied for a long time. Dudley, who also wrote some of the first upper bounds on the Wasserstein distance, uh, studied empirical processes for a very long time. And so we will use a bound from there, and we'll see how it gives us these rates of convergence. So I will just state something. It's called Dudley's chaining bound. You can, again, look this up easily. It's a very famous result in empirical process theory. And maybe let me just say intuitively what's going on, right? So if I take one average minus an expected value, you would just apply something like Hoeffding's bound. If I say now take a finite collection of functions and do average minus expected value, this is the argument we did before. You would do a Hoeffding bound with a union bound. If I give you an infinite collection, so there are infinitely many one Lipschitz functions, then you have to be a little bit more careful. So you would first apply some sort of discretization argument, then take a union bound, and then maybe try to argue that if two functions are very close, then these values should be quite close, so they cannot affect the supremum too much. So as long as I can control it over an appropriate discretization, I'm still okay. And then chaining will say, okay, you should do this multi-resolution discretization, and that will also more tightly control the supremum of an empirical process. So now let me state the bound. This is just a general bound. You can find this in many references. Suppose I give you some collection of functions. They're all bounded by R. Then the expected supremum of an empirical process, and so a term that looks like what we wrote, is always upper bounded by the following quantity. I can pick any resolution tau that I want. I can sort of cut off the process, cut off my discretization at that tau. And then you get something which is called the entropy integral of your class of functions, which in this case will look like this. It's the integral from this of the square root of the log of the covering number of your collection of functions. Right, so I will state this. Okay, so this is the chaining bound. So what is the covering number of your collection of functions? It's just it's the minimum of the cardinality of a subset of functions such that let's say f forms an epsilon cover. What does this mean? So f is some collection of functions, let's say f1 through fn. Then what does it mean to form an epsilon cover? It just means that for any function in my class, the min over j of the distance between f and fj, say in the L infinity norm, is at most epsilon, right? So that I can, for any function in my class, I can find an element of my cover that's within epsilon in the L infinity distance. The minimum cardinality of such a cover is the covering number. So it's somehow the most parsimonious cover that I can construct, the size of that. And the Dudley's chaining bound just says something like the square root of the log of that covering number determines the expected supremum, or upper bounds the expected supremum of an empirical process. Okay, maybe a picture. So if you have some collection of functions, a cover is just some collection of discrete elements. So this is, and then you should imagine putting an epsilon ball around each of them. And then if it's a valid cover, then these epsilon radius balls around each of these things should totally cover your collection of functions. Okay, so let me just pause and see if people have questions about Dudley's chaining bound.
Aren't these the same set of ideas used to prove supremum of the case distance between empirical f of xi minus expected f? I think they do the same things there.
Sure, yes. I mean, yeah, I guess you mean the ks distance in one dimension you can write in this way as a supremum over, I don't know what, left intervals of f of x minus the expected value of x, and then you could use some similar technique to bound that expected supremum. Yes.
Right. Yeah. Okay.
And yeah, so almost every bound in the analysis of empirical risk minimization and so on will pass through some argument like this at some point. So if you want to do something like a union bound over an infinite collection, at some point you will invoke some argument that looks like this chaining bound.
Now, this infinity norm is essential, or could you do similar arguments with other norms?
You can try to do similar arguments with other norms, but you'll have to make more assumptions about the underlying random variables, and potentially you will need something like sub-Gaussianity somewhere and so on. So this is maybe the cleanest version of this. There are other versions where you cover in other norms, but you do have to be a bit careful. It usually will require an empirical norm cover, and then you'll have to say the empirical norm cover can be constructed. And so there are not maybe very clean generalizations that don't use the infinity norm. But there are generalizations, yes.
I see. Okay, thanks.
Yep. Okay, so now, okay, let's go back to what we were trying to do. So in order to apply this, we're trying to apply this chaining bound to the class of one Lipschitz function. So one needs to calculate the covering number. So remember, we're working on the unit cube. So mu is supported on the unit cube. And you can, without loss of generality, just take you can subtract a constant so that your Lipschitz functions, say, all take the value 0 at the origin. Right, so the empirical process or the quantity, the W1 distance is invariant to some shifting, so I can just define it, take my functions to be 0 at the origin. And so they're all one Lipschitz and they're 0 at the origin, so they're all bounded by some constant. So that is all of my, they're all bounded by some number. Okay, we'll just, yeah, some are. Okay, so there's some constant so that all of my functions are bounded. And then under these conditions, we also know covering numbers for the collection of Lipschitz functions. In particular, you can find that the covering number for the class of one Lipschitz functions scales like, again, I will drop the dependence on R, scales like 1 over epsilon to the D. Right? So in D dimensions, the log of the covering number scales like 1 over epsilon to the D. Okay, so this is just a, you can prove this by explicitly constructing this cover. It's not a difficult thing, but let's just, for us, we'll just take this as given that the covering numbers scale like 1 over epsilon to the D, and then we'll try to see, okay, what is the implication for us for the Wasserstein distance? Everyone okay with this? Okay, so then let's just do the calculation. So we're trying to upper bound the expected Wasserstein distance. So let's first do the D equals 1 case, the expected Wasserstein W1 distance between mu n and mu. By Dudley's bound, it's less than, I can pick any tau that I like, right? So it's less than, I'll take tau to be 0 in this case. Then I have to integrate from 0 to some radius, the square root of the covering number, square root of the log of the covering number, which in this case would be 1 over square root epsilon d epsilon. And then there's a 1 over root n sitting outside.
So is the size of that cover n epsilon if after taking log would not be 1 by d log 1 by epsilon?
No, that is, it's a non-parametric class. So you would get log 1 by epsilon type covering numbers if it was a parametric class. That is, if it was just D real numbers or D-dimensional parametric class would have what you just said. This is a non-parametric class, so the log covering number scales the way I said.
Okay.
So
Thanks.
the actual covering number looks like 2 to the 1 over epsilon to the D.
Thanks.
Okay, so good. So this integral is some constant, so it will look like 1 by root n, which is what we wanted. So this is the d equals 1 case. The d equals 2 case, you have to take a different value for this truncation, so we'll pick tau to be n to the minus 1 over d. Then we would look at this quantity, which will be less than n to the minus 1 over d. So when d is 2, the integral is starting to diverge, right? So it looks like the integral of 1 over epsilon d epsilon, and we've truncated it at some level n to the minus 1 over d, and it goes up to some r, right? So now this piece of this integral will exactly contribute some log factor, and so these two terms will totally contribute something that will look like log n over square root n. So in this case, again, the entropy integral diverges, so you have to be careful to truncate it at an appropriate level, otherwise the whole thing will just blow up. And now when you do this calculation, you will end up with this thing that it will scale like log n over square root n. And remember, when I stated the bound, I told you that the correct thing is it should scale like square root log n over n. This is the correct rate. And it turns out that this technique will not give you that rate. And this is why it's a very famous paper in probability called the AKT theorem, which kind of tells you how to shave off this extra square root log factor. But it's very technical. So this is the other case. Okay, at least chaining will give you something. It'll give you a suboptimal log factor here. And then once d is bigger than 2, you can do the same argument. You would again take this truncation to be n to the minus 1 over d. And once again, your entropy integral will diverge. And you will. So now you have to integrate epsilon to the d over 2 from from here to there. And you can again do this integral. It's just something, it'll work out to be, maybe it will look like this. It's d over 2 minus 1, right? So it will look like, and this will scale like n to the minus 1 over d. Okay, so the punchline is just that, okay, you can do these entropy integrals once you have these covering numbers, and they will tell you that the Wasserstein distance between the empirical measure and the truth will, at least in high dimensions, will scale like n to the minus 1 over d. Okay, let me pause here for a second and see if there are questions. Okay, so we have basically proved the result for W1 that we stated up here. That's this one, up to one of these log factors. Now, maybe one can ask two questions. One of them is, what do you do for general WP? Because you don't have this nice dual representation. And the other question maybe is, how tight are these bounds? And so we'll try to answer these two questions. One of them is a bit easier to do, so let me do that first. So let's first try to understand why n to the minus 1 over d, at least roughly, should be the right rate for the empirical measure. And from this argument, you will also see why the empirical measure doesn't adapt to smoothness. So let's try to understand this case. So let's think about the following setting. Let's say mu is some nice smooth distribution. It looks like, let's say, the uniform distribution. You can take any distribution essentially that is sufficiently spread out, and you will end up with the same lower bound. So think about it's the uniform distribution on 0, 1 to the d. And now I want to convince you that the Wasserstein distance, so I want some sort of lower bound on the Wasserstein distance between mu n and mu. And I want to say it's at least something like n to the minus 1 over d when d is big. Right, so how do I convince you of this fact? Right, so one way to try to convince you of this fact is to demonstrate a one Lipschitz function. So this is at least, I can pick any one Lipschitz function, and then it will be the expected value of f minus the average of f. So I'm going to now try to pick a clever one Lipschitz function that makes this contrast pretty big. Okay, so we'll choose the following function. The function is going to be the distance between x and its nearest neighbor in the sample. Okay, so this is my one Lipschitz function. So let's, I don't know, we can check that it's one Lipschitz by saying, okay, what is this function exactly? It's the min over j of x minus xj. Right, and each of these is a one Lipschitz function. And so its minimum is also a one Lipschitz function. Right, so I've constructed now some one Lipschitz function, and we can try to reason about how big this term is. Okay, so let's try to do it. So I claim that it's the second term, the distance of each sample point to its nearest neighbor is just 0, right? So the average part is 0. So it's at least the expected value of this function. Right? So it's at least the expected nearest neighbor distance. So this is a lower bound on the W1 distance. Is everyone okay so far? Okay, so this, maybe you have seen this argument before, but this is the expected nearest neighbor distance. At least intuitively, you should believe that, I don't know, if my uniform sample kind of looked like a grid, then it would be the case that every point, the nearest sample point should be roughly n to the minus 1 over d away. And so there's some standard argument that one can use. You can calculate this fairly precisely, but for us, we'll just care that some intuitive argument that if I thought of a uniform sample as roughly like a grid, then every point would be at least n to the minus 1 over d from its nearest neighbor. So the expected nearest neighbor distance, in fact, does scale like this. Okay, let me pause here and see if people have questions. So this is just saying, okay, this bound that we proved for the empirical measure, it's relatively tight. At least in the d bigger than 2 case, you can see that it's quite tight. Questions?
Can you go over that inequality again? Why W1 mu and comma mu is greater than expectation of F?
So, okay, so I'm saying the W1 mu and mu is at least it is exactly the supremum over all one Lipschitz functions of this difference. So in particular, it is at least as big as this value for any one Lipschitz function. I can take any one Lipschitz function that I like, and it's, okay, let me call that F tilde, as provided F tilde is Lipschitz, right? So I'm just saying the supremum is at least as big as one of these and now I will choose that one function, and I'm particularly choosing this function. This function is the distance from a point to its nearest neighbor in the sample. It has average 0 because every sample point is its own nearest neighbor. So it has value 0 for this function. And so we just need to calculate the expected value of this function, which is, suppose I draw n samples from the uniform measure, and then I say, now I draw another new sample and say, what is the distance I expect for that new sample to the nearest neighbor in the first n samples? And that will scale like n to the minus 1 over d.
Yeah, I get it. Thank you.
So Shiva, for this function, if we were just to do central limit theorem, I guess, you see square root of n convergence rate, and then you see the variance. And I guess what you're saying is that somehow the variance is scaling with dimension.
No, so this is not a fixed function a priori, right? So that is, it's a sample dependent function. So you cannot apply the CLT like that.
Uh-huh.
So I'm using the fact that as long as it's a one Lipschitz function, it's in my collection. But if I just took it as a fixed function, it's a bounded function, the variance would be bounded, and the average would be, yeah, it would just be 1 over root n for any fixed function. The thing that I'm doing is I'm picking a sample dependent function, but I'm allowed to do this as long as it's in my class.
I see. So when you have this in the definition of W1, you were allowed to have sample dependent functions.
Yeah, they can be anything as long as they are one Lipschitz.
I see.
Yeah. Okay, great. Other questions? Okay, so the last thing that we'll do is to talk about the other way that people upper bound the Wasserstein distances. And it's a kind of cute argument. We'll try to understand it. It's a somewhat more robust argument than trying to rely on duality to do it. So it's very closely connected, but so it's called the dyadic partitioning argument. So this will not use any particular structure of W1, so it will be a more generalizable argument. So maybe philosophically, what are we going to do? So we want to somehow argue that the WP distance between mu n and mu, or more generally, I give you just some pair of distributions, and I want to argue that the WP distance, let's say, is small. in order to argue this, it is sufficient to construct a coupling between these distributions. So the WP distance is the cost of the best coupling. So as long as I can demonstrate some coupling that has small cost, I know that that gives me certifies an upper bound on the Wasserstein distance. So it is sufficient to construct an explicit coupling, to somehow construct a coupling between these two measures to certify an upper bound. So we'll construct a coupling and maybe try to say what is its cost. Okay. Good. So let me state the lemma, and then we'll try to interpret it. Like proving it very formally takes a lot of notation, so I won't do it. But here's what you should imagine. I'm going to say start off with the unit cube, and I'm going to successively dyadically partition it. So we'll start off with the unit cube, then I will split it up in two, and then I will keep refining these. Okay, so we'll go through, and there's actually some connection between this and chaining, but you should maybe think of this as the primal counterpart to chaining. But I'm going to keep constructing these partitions. So this is at some level, let's say this is k equals 1, this is k equals 2, and so on. We'll keep going down in levels, and we'll keep successively refining our partition. And so let me call the collection of pieces here, let's say q sub k, right? So that's the collection of these cubes at the level k. And the lemma just says, if I want to know for any pair of measures, I can say, let's say I want to bound the WP distance between mu and nu. It's always upper bounded by the following quantity. So I pick some capital K, which is some maximum resolution. I'm just going to go down up to the resolution capital K. Then it's upper bounded by 2 to the minus kp plus the sum over little k going from 1 through capital K of 2 to the minus little k times p times another sum. And I'll help you parse this in 1 second. In this collection, let's say qk, I look at each of the cubes and I say, how different are mu and nu along that cube, right? In the TV sense. So what's the TV distance between mu and nu at each resolution? And this gives an upper bound on the WP distance. And so now let me relate it to this thing that I said, somehow I'm constructing a coupling, and let me try to explain what's going on. So you should imagine our argument is going to go the following way. At the first resolution, we are just going to, both the measures integrate to 1 on the whole cube, so we can forget about that one. Now we move over to the second picture. And what we're going to do is we're just going to fix the errors at the level of these big cubes. So maybe there's some, we'll compute mu q minus q. So maybe mu puts more mass here, then I have to take that extra mass and move it somewhere else. So I'm going to take that extra mass and figure out where to move it. That will tell me how my coupling works, right? So whatever it is, this amount of extra mass. So at this resolution, I'm going to fix the errors in the between. I'm going to fix the errors between the two distributions. So there's some amount of mass mu q minus nu q, and those all will have to travel this distance. They will go to some adjacent cube somewhere. Right? So that's the cost I will pay for fixing the errors at this resolution. Then I go one resolution further down. Now I only need to fix the errors at that resolution. So there will be potentially more errors to fix at lower resolutions, but they will only have to travel a smaller distance. And so this is maybe how one should think about this upper bound. So you think about it as I fix errors at the coarser resolutions, then I go down a little bit and I fix the errors or the different discrepancies in the distributions at that level and then keep going down. And this is maybe also one way to just interpret the Wasserstein distances, at least. It is an upper bound on the Wasserstein distance, which is some sort of multi-resolution TV. It's like the TV distance, but it's like a coarsened TV distance, and you combine those coarsened TV distances with appropriate weighting factors, and that's what gives you somehow some reasonable upper bounds on the Wasserstein distance. So proving this formally just requires a lot of notation, but let me see if people roughly get what's the intuition of the bound.
So you will choose the coupling that is average over all these Ks, right? Q1 plus Q2 plus Q3 dot 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 by K. That will be the coupling you'll upper bound this WP by.
The coupling sort of, I don't know, it's somehow implicitly defined here, but it says take a piece of mass and uh, just, yeah, you track through where it goes according to this. That is, if you can fix it at some lower resolution, you stop moving the mass there. But otherwise, maybe some pieces of mass have to move all the way over. So somehow, yeah, this amount of mass will move from some place to an adjacent cube, but then there's some smaller amount of mass that will move within these little cubes and so on. It's a little bit hard to kind of formally describe this coupling fully. But there is a coupling that will witness this upper bound. But there isn't an averaging over levels going on. Okay.
You said this is a way to think about Weissenstein metric in general, right? So with some extra terms, is this tight almost?
No.
I see.
It'll turn out that it's tight when mu and nu are very close. So the case when mu n is an empirical measure drawn from mu, it'll turn out to be approximately tight. In general, you should not expect it to be tight because
Yeah, at each level you're wasting too much.
yeah, but also I can sort of adversarially position one of these distributions so that they're all right. Like, I don't know, can imagine that mu puts all its mass near one of the boundaries, and then nu puts all of its mass on the adjacent one. The actual Wasserstein distance pays a very little cost, but this dyadic coupling will say, okay, I have to match across two very coarse resolution cubes, so it'll be a very large upper bound. And so you can maybe construct measures for which this is nowhere near tight. There are cases that people have tried to study the following thing, which is if I did not commit to this dyadic partition a priori, but rather sort of randomly placed a grid, then you can also lower bound the Wasserstein distance by something that looks like the average over a randomly placed grid of some quantity that looks like the thing on the right. So I think of it as a useful tool for reasoning about the empirical measure to the truth, and then otherwise it can be a relatively loose upper bound.
Thank you.
Okay, so maybe in the last few minutes, I will just tell you how maybe roughly one should use a bound like this to get at least let's try to understand what happens. Say d is bigger than 2. Let's say that mu is the uniform distribution, and let's say that I want to bound W1, right? So let's say I want to look at W1 between mu n and mu, right? So, and you can just use this bound and say it's less than 2 to the minus k. Plus now we have to say, okay, what happens to all these terms? And we'll just do some back of the envelope type calculation. So there's a 2 to the minus little k here. And now I need to reason about this term, which is these TV-like discrepancies, right? And I claim that mu n of q minus mu of q should roughly behave like this is just some sort of Bernstein inequality will tell you that it should behave like the variance. It's just a binomial, should behave like the variance, which will look like mu of q divided by root n. Right? So this is by Bernstein. And so you should imagine that the measure of one of these cubes at the at the kth level will look like something like 2 to the minus k times d, right? So this is the side length raised to the dth power. So this term mu q divided by n looks like this. It'll scale like that. And the other question is, okay, at the resolution k, how many cubes do I have? I have to sum over all of them. That will contribute some factor, which will look like 1 over 2 to the minus kd, right? So there are 2 to the kd cubes. And so that's roughly how this bound will scale. And if you do this calculation, you will pick capital K to be something like log n over d. And then this upper bound will scale exactly like n to the minus 1 over d. So this is just saying the way that one bounds this, it is perhaps much more natural. It just says, look at all these cubes and say, what is the empirical to population deviation along these cubes? And then you put it all together and you get a bound. And you can see that there's nothing very specific to W1 being used. This dyadic partitioning bound works for any WP. And so you can do exactly the same argument and you will get these rates for general WP as well. Okay, so this is, I think, where I will stop for today. So if there are questions, I'm happy to answer them.
Any questions?
What does this method give you for d equal to 2?
It'll give you the same thing that chaining would give you. It'll give you log n
Log n
over
by square root n.
Yeah.
I see.
You can also ask other questions about optimal transport since this is the last session.
Here, when k tends to infinity, does this right-hand side converge to something?
Not always. It's that is when d is equal to 1, it will converge, but maybe you should imagine that when d is bigger than 1, it'll behave exactly like the entropy integral. That is, you can somehow view all of these terms as analogous to some term in Dudley's bound. But if you don't truncate it, that is, you take k equals infinity, then the right-hand side for the empirical measure when d is bigger than 2 will not converge. And you can sort of see it here. Maybe I'll tell you what this is. So that is this term, if you work it all out, will scale like 2 to the k times d over 2 minus 1 divided by root n. And so if you take k to be infinity, it'll just blow up.
Thanks.
Yeah.
Sir, some open problems in the field?
Oh yeah, there are many. So maybe yeah, okay. So some of them are like sort of practical ones, which are, I don't know, for instance, these transport map estimators that we know how to analyze are quite impractical. And what people do in practice, this is why this whole all of these things like rectified flow and flow matching and all of these things exist, is that they are somehow much more practical algorithms to compute things that resemble transport maps. And so one question generally is to try to analyze those more practical things. The same way, I think there are lots of open questions on Wasserstein density estimation. Once again, the estimators which use kernels and things like that are not very practical in high dimensions. We have very little understanding of the smooth case of Wasserstein density estimation. So I think of that as also a very nice problem to try to just construct better density estimators and try to robustify the arguments that we have. We have some set of arguments, but they're kind of brittle. And so that's one thing. The other is I talked mainly about statistical estimation. The other thing that statisticians often care about is inference. So what does inference mean? I don't just want to say here's the rate of convergence. I want to say what is the limiting distribution when you rescale it in the right way. And if you can figure out the limiting distribution, you can use it to construct confidence intervals. You can use it to do hypothesis tests and so on. And so one can ask things like, I don't know, is there some scaling of the transport map such that when I rescale by that amount, then this thing converges in distribution to something, and what is this distribution, and so on. So these are like kind of inferential questions. They are much harder than these estimation questions. And again, I think it's a very big open question as to like how do you do reliable inference for all of these various objects that come up in OT. And generally, one thing that seems to be the case is that the reason why practitioners like the optimal transport framework is that it's kind of robust in the sense that you don't need to do smoothing. You can estimate all these objects without too much trouble. And it seems not very brittle as a tool for data analysis. It's like the distance is well defined between empirical and true measures and so on. So there's some nice properties that it has. But often in the statistical side of it, if you want to reason about the statistical properties, it seems like you need a lot of new assumptions on top of it, right? And you need all these like Brenner regularity assumptions and stability type assumptions and so on. So even though the objects are well defined with very few assumptions, to estimate them well, you need a lot of assumptions. And so the kind of trying to close that gap is I think, the general high level, big open question in the field.
Okay, so thank you.
Sure, one quick question. In this
Yeah.
diffusion modeling, you start with some samples and you generate samples from the same distribution. And now you want to do some testing of hypotheses to say that they are from the same distribution. What's a good test that makes sense here?
Yeah, there are many, but maybe one would be to just calculate the Wasserstein distance between the generated samples and say some ground truth samples. And then you have to determine some cutoff, but say you can use something like a permutation test to determine a cutoff, but that would be a sensible thing. What might happen in practice is that the Wasserstein distance is too powerful. That is, it's going to be very large in high dimensions between your generated samples and the true samples, but it might also be large between like subsets of the true samples. Like it's just a very strong metric. So you might choose to try to weaken the Wasserstein metric in some ways. And so one thing that people do is you can compute something called the sliced Wasserstein distance, where you project it on various dimensions and then you compute the Wasserstein distance of these lower dimensional projections and put it together. So I don't know. So maybe the high level answer is you could compute the Wasserstein distance and do a two sample test. It might be too powerful a test in the sense that that distance maybe is too sensitive in high dimensions. And so maybe a better thing to do would be to try to think about projections and then computing Wasserstein distances between projections and things like that. Or compute something like the entropic distance, which is again some regularized version of this distance.
Okay. Good, thanks.
Thank you.
I guess I have two questions. One is a stupid question that, so when you said that you can do inference by trying to figure out the correct scaling so that the difference is between the estimated and the true map that you can capture. So what does this have to do with inference? Like, I just didn't get this at all.
So what is, I guess maybe inference is a loosely used term, but one thing that I could try to say is I want to construct some maybe somewhat sensible interval so that like a confidence interval so that I can say, okay, the probability, let's say we do it for the Wasserstein distance. So that is the probability that the Wasserstein distance between mu and nu is in my set C alpha is at least 1 over alpha, 1 minus alpha, right? So this is a confidence interval for the Wasserstein distance. So I want to construct using samples some set C alpha. somehow captures appropriately my uncertainty in how well I've estimated this distance. And the way that statisticians do this, so you can say, okay, if I know the rate of convergence, then I can somehow loosely construct such an interval. But that's not the way that people normally do this. If you want it to be a practical procedure, you probably want to say that there's some scaling such that I don't know, your estimate, say, minus this thing converges, say, in some in distribution to a normal 0, 1 or something like that. And then from this limiting distribution statement, I can construct something that will, from here, I can construct something so that the at least asymptotic coverage is correct. I don't know, is in the set, which is W hat plus or minus something. Divided by Rn is at least 1 minus alpha. Right? So the practical way that people do inference is, so I want to construct an interval that catches the truth with some probability. The usual way that people do this is you try to characterize the limiting distribution of your estimate minus the truth.
And one more question. So you had this idea of expressing the Wasserstein distance, at least for the W1, if I'm not wrong, as an integral probability metric. So in that metric, the class of functions was the set of one Lipschitz functions. So is there also like some good theory or it makes sense to do same thing for maybe other classes? So let's say maybe the class is neural networks.
Yeah, so that is, you can define IPMs with some class of neural networks, and it will define for you a discrepancy, and you can do the same things that way. And people do two sample testing, for example, with some principle like that. That is one, again, practical way to try to do two sample testing is to try to design a classifier that tries to classify between the two samples that I've given you. And if it can do so better than chance, then you know the distributions are different. That is, in effect, trying to design an IPM which is based on your class of functions that you're optimizing with your neural net. So yes, you can do things like this too.
And then for that also, is it like a way to do the duality thing you did?
So I guess maybe one should back up. So you can define IPMs generally, and you can use them. That is, you can say, I will define a distance between mu and nu to be the supremum over some class of functions. So that is, you start already in the dual.
Yeah, you start with the dual, exactly.
Whether these will have sort of
some primal
none
interpretation.
of these will have nice primal interpretations, and I think maybe W1 is the only one that has a very nice sort of moving mass interpretation like this. I don't think that if I just generally threw down a function class, there isn't a good reason why it should have a nice primal interpretation. I mean, it's not even clear. Yeah, I don't know what that would mean, but I don't think they. Yeah.
Okay. I guess next question. Okay. Any further questions? It's fine. Last question. Okay. No more. So let's thank the speaker.
Thank you.
Okay. So thanks again, Tiva, for the awesome bootcamp. I think people are prepared for next week now. So yeah. Thanks and have a good day.
Thank you.